Good morning, everybody. We'll just get started in a few minutes here for our GOA-ON webinar series. Let people trickle in. Thank you for joining, everybody. We'll get started in just a minute or so. Let people join from across the world here. Okay, I see we're now 2 minutes past the top of the hour, and it looks like our attendee rate has kind of settled in. So we're going to go ahead and get started here. Welcome to the GOA-ON Webinar series for our December webinar series, the last in 2020. We just want to thank you for joining, taking your time to listen to 2 great presentations that we have lined up for you today. My name is Gabby Kitch. I'm with NOAA's Ocean Acidification Program and one of the GOA-ON Secretariat members, and I'll be moderating today's webinar. This webinar series has 4 sponsoring organizations. First, GOA-ON, the Global Ocean Acidification Observing Network. Second, NOAA, the National Oceanic and Atmospheric Administration, my home base. Third, the IAEA OAICC, or the International Atomic Energy Agency Ocean Acidification International Coordination Center. And the IOC UNESCO, the Intergovernmental Oceanographic Commission of the United Nations Educational, Scientific, and Cultural Organization. For those of you who are new to GOA-ON, first of all, welcome. It is a collaborative international network of over 900 members from 105 different countries and territories. GOA-ON's mission is dedicated to detecting and understanding the drivers of ocean acidification and the resulting impacts on marine ecosystems. During this presentation, you all will be in listen-only mode. So if you have any questions during the presentation, feel free to type them into the questions box that you will see on your Zoom screen, the Q&A box, and we will present those questions to the speakers at the end of the webinar. So we'll have 2 presentations and then a Q&A session afterwards. At this time, I would like to introduce our speakers for today. We have Professor Margaret Mgundari, who is a lecturer at the Department of Marine Science and Technology at the Federal University of Technology in Nigeria. She received her PhD in Earth Sciences in 2020, and her thesis focused on the carbon solubility pump, carbon dioxide flux, and ocean acidification below Southern Africa, South Africa. And she got her PhD in South Africa, excuse me. Currently, she is working on writing more papers from her PhD thesis on the project sponsored by the Ocean Foundation on baseline coastal ocean acidification monitoring in the Gulf of Guinea. For our second presenter, we have Dr. Mohammed Ahmad. He is now a higher education specialist at Esri, Canada. Mohammed received his PhD from the University of Calgary in 2020, where he focused on budgeting the marine carbon sink in the Canadian Arctic waters. Then he did 2 short postdocs at the University of Calgary and the University of Victoria, studying the air-sea gas exchange and impacts of climate change. So these two speakers today make up our collective webinar series entitled Carbon Cycle Monitoring in Extreme Latitudes, focused on the Southern Ocean, Margaret, and the Arctic Ocean, Mohammed. And before we get started, I just want to make a note that to stay tuned for a January webinar. Our 2023 webinar series will be kicking off in January. For 2023, we have a special lineup for you all focused on each of the GOA-ON regional hubs, where the regional hubs will facilitate bringing or showcasing science from their region or scientists from their region. So if you would like to receive announcements about this January webinar, be sure to join as a GOA-ON member. Maybe my counterparts on the Secretariat can drop the link of where to become a member in the chat, and you will receive some notifications about this webinar. So with that, I will stop sharing my screen and pass it along to Margaret to start her presentation. Margaret, whenever you're ready. Perfect. Looks great. Beautiful. And Margaret, I still have you muted on my screen. Great.
Okay, hello everyone. Thank you, Gabby, for the powerful introduction. And I can see you have already promoted me to the post of a professor. So, and that is okay. It's very, very okay. Thank you so much for the introduction. So, good evening, everyone from over here in Nigeria. I'll be talking to you on winter carbonate properties in the Southern Ocean, south of Africa. And what I mean here by south of Africa is that the Southern Ocean defined here is south of 35 degrees south.
You may need to use your keyboard, Margaret.
Yeah, I'm doing the keyboard. It's not going. Wondering why.
In the bottom left side or bottom right hand side of your screen, is there a manual way to toggle between slides?
Mm-hmm. Yeah. Okay. Good, perfect. So I said I'll be talking on winter carbonate properties in the Southern Ocean, south of Africa. What I meant here by south of Africa is that the Southern Ocean is defined as south of 35 degrees south, as we can see it here. And the data I will be talking on were observation of carbon dioxide system made during the Southern Ocean Seasonal Experiment Winter Cruise in 2019, acronymed as SCALE 2019. This work actually formed part of my PhD, and we are working on it for journal publication. So by way of introduction, The carbon dioxide system in the Southern Ocean south of 35 degrees south is key to predicting the future ocean carbon uptake in the changing climate. And this is because of the formation of fronts. As we see the formation of fronts in the Southern Ocean, and also the overturning circulation pattern in the Southern Ocean, which provide efficient pathways that enhance the uptake of carbon dioxide from the atmosphere, so that much of the carbon dioxide absorbed by the global ocean is taken up actually in the Southern Ocean. And this overturning circulation is made up of two cells, the upper cell upwelling of upper circumpolar deep water and northward Ekman transport of the nutrient carbon dioxide rich water, which are utilized by phytoplanktons and enhance the drawdown of carbon dioxide from the atmosphere. And then the second part is driven by the dense water formation near the Antarctic continent, which also draw down carbon dioxide to the deep. But unfortunately, this region is summer biased observation, lacks seasonal observation, especially during the winter seasons. Thus, we have an incomplete understanding remaining for the actual evolution of the marine carbonate system and the corresponding seawater acidification. Therefore, this study actually provides us with new winter carbon dioxide system observations, a season where observations are very, very sparse. Also, using this data, we're able to carry out internal consistency of the carbonate variables, that is the fugacity of carbon dioxide, the total alkalinity, dissolved inorganic carbon, and pH. Because on this cruise, we're able to measure all these 4 measurable parameters or carbonate parameters, and it helps us to carry out this internal consistency of carbonate variables. And also, it is also useful because being winter season, where we expect little or no significant biological productivity that will interrupt the carbonate reactions or the carbonate activity, the inorganic carbonate activity going on. Also, from the calculations, we are able to also calculate the aragonite saturation, that is the omega, which is an indicator, we have an indicator of the biological impact of ocean carbon, ocean acidification. It was calculated alongside the Revel factor, which also quantifies the ocean sensitivity to increase in atmospheric carbon dioxide. So the parameters measured, as have been mentioned, we measured the sea surface fugacity of carbon dioxide in water using the continuous underway sampling method. And we sampled the dissolving organic carbon dioxide and total alkalinity and pH, also surface parameters using the discrete underway sampling. The TA and the DIC were measured using the Vinter equipment, while the pH on a total scale was measured using the spectrophotometer. And here I have the map of the cruise going from South Africa down south, and it was actually on a return transit, and measurements were carried out during both the southward and northbound transits. So I have the results. Here we have the distribution of the sea surface carbon dioxide in the upper panel, showing high variability there. And so we decided to do the running mean to smoothen the data. We see the values ranging between 370 to 432 microatmosphere. And we see the flux distribution, that is the carbon dioxide flux distribution in the lower panel, that is a C and D. We see it's ranging between the values here, negative values showing us the carbon dioxide flux into the ocean, that is what we call the ocean carbon sink. while the positive values showing us the carbon dioxide flows going from the ocean into the atmosphere, which we call the carbon source, ocean carbon source. One noticeable event here is the more of carbon sink that were observed during the during the northbound transit in the subtropic, where we have just a 2 weeks lag, and we are observing more carbon dioxide absorption into the ocean, that is carbon dioxide sink in the subtropic. Well, we have some nutrient data also collected, checking into the nutrient data to see if there's some kind of productivity. We found out that there's no much significant differences, but looking into satellite data of the MODIS Aqua from NASA, we try to check into the months that we are concerned about. That is, the southbound transit took place in July, while the northbound transit took place in August. And observing it, we can see there seems to be like much intensity of the chlorophyll, the mean chlorophyll concentration during August, which we can probably say that was the result of the higher or the more carbon sink that was observed in the subtropic region. For the discrete water sample, discrete parameter distribution, we have the DIC. We can see the DIC, the distribution ranging between 2,036 to 2,203 micromole per kilogram. And we see the distribution degradation going with like temperature. We have low DIC in the region of the subtropic, where we have high temperature, while we have high DIC in the region of lower temperature in the weather jet. But for the total alkalinity, we see the variability. It follows the variability of salinity, the sea surface salinity, where we can say that we have higher TA values in the saltier waters. And for the pH on a total scale during the cruise is like an overall decreasing trend southward. That is, you have lower values in the tropics and higher values in the weather GA domain, where you have low temperature. So this is the distribution we have from the discrete samples. Now I go to the internal consistency assessment, where we have to recalculate the carbonate variables. That is, these 4 carbonate variables. We recalculate them using the carbon dioxide Excel sheet, and each of the parameters were calculated as a function of input of the 3 other pair of the other parameters. E.g., when we're calculating the pH, we calculate from the pairs of the FCO2 DIC, the pairs of TA DIC, and the pair of FCO2 TE, which also occur for the remaining 3. And here we use, for the recalculation, we use the carbonic acid constants of Mebat et al. 1973 as refilled by the Dixon and Millero 1987, and of Goyet and Poison 1989. And the intention here is to look between the results from these two different acidic carbonic acid constants, because they were actually derived from different media of seawater. The first derived from natural seawater, while the second were derived from artificial seawater. So going further, after the calculation has been done, so the assessment is by the residual. The residual now derived from the difference between the measured variable and the calculated variable. So the smaller the residual value, we say the better the accuracy. That is, the better the accuracy of the measured value. And this is with an implicit assumption that the measured values are the true values. Here I show the distribution, a box plot distribution of the residuals for FCO2 and pH, and as we can see, each for the carbonic acid constants. And what we observe here is that we have high values of the residual for the pair of input pair of CA and DIC, both for the calculations of FCO2 and pH. And here we are able to observe that the carbonic acid constants have maybe little or no significant impact on the calculations of these parameters, because we can see they are all looking very similar. If we look between the FCO2 calculated from the Maybach constant and that calculated from the GOAON constant. So for this, we can say that the carbonic acid do not have any, maybe do not have significant influence on any form of uncertainty that we might expect from this recalculation. Then if we looking at the total alkalinity and DIC, we'll see also we have large residuals when we have the total alkalinity and DIC calculated from the pairs of FCO2 and pH. So, and again, another observation we have here is that the TA and the DIC residuals are like oppositely equivalent. And what I mean by that, you see the residuals here for the TA, they are positive, while all of the residuals for the DIC, they are negative. So it's like they are equivalent sort of, but oppositely equivalent. So again, here we also see that the influence of the carbonic acid constant is not very significant. And so if we are expecting uncertainty in the recalculation of these parameters, then we have to look into the different input parameters, which is actually a work also we are trying, that is we are doing also on this study, so that when we are taking it out for publication, we include that to see if where the uncertainty is actually resting. So I have now the aragonite saturation, which is the omega, which I have said, as I said, is an indication of the impact of ocean acidification. So this is the distribution from the different pair of calculation, because remember I said that these are derived carbonate parameters which were calculated along the recalculation of the four other parameters. So if we look at this distribution, this Bose plot distribution, we see that the values are also high for the input pair when you use the total alkalinity and DIC, both for the omega and the RF. So in NS, what we have observed from this recalculation is that for a pair of the parameters, you may need to measure and recalculate maybe the other ones, because actually why this study is actually important is because most of the times these four variables or these four carbonate parameters are not seem to be measured on from one or maybe from one sampling procedure or from a particular cruise. So most times what happens is that we measure two of these parameters and then we calculate the remaining two, just as the procedures I have mentioned above. So for this now, we'll look at it that we have to be concerned about the best pair of input parameters. That is, we have to look into which of these two will give us a best result or more accurate result. And that is the reason why this internal consistency study has actually been carried out, or has actually been done severally in other regions and by other studies that have been carried out. So again, what we observe here is that the omega now is ranging between, the distribution of the values is ranging between 0.5 to 3.7. And we know that the omega value, there's biological impacts significance is that omega value equal to 1 is saturation. So it means that when as we are below 1, we are already having under saturation occurring. And okay, I'm not showing the distribution here, the latitudinal distribution here, but we'll find out that the lower values occur in the region where we have high values of RF. And also, as I have said, we have high values of the omega when we have the impute pair of total alkalinity and DIC. So in conclusion, we say that the winter surface aragonite under saturation is occurring in the Weddell GA with high Revel factor when compared to previous studies, which may be due to winter mixing that is causing higher DIC in the surface ocean. And also the best pair determined in this study for the carbonate variables calculations are as given. The FCO2, the best pair is the pair of DIC and pH. Then for pH, the best pair is the pair of FCO2 and DIC, or FCO2 and total alkalinity. Then for total alkalinity, the best pair from our determination here is DIC, the pair of DIC and pH. And for DIC, it's the pair of total alkalinity and pH. And also, as we saw in the distribution, the internal consistency of DIC from total alkalinity and FCO2, total alkalinity and pH, and of TA from DIC and FCO2 and DIC and pH are equivalent. So, and what I mean by this equivalent, I mean that one can be used for the other. So in case you are able to measure the DIC, it's may not be necessary for you to do internal consistency for total alkalinity if you have done for a DIC, because they are just like oppositely equivalent. So thank you for listening. Thank you very much for listening. And I want to acknowledge the following people: Professor Roy, Dr. Warren, my supervisors, my PhD supervisors, Dr. Susan Fietz, my colleague in South Africa, and Dr. Agnita Franson and Dr. Melissa Cherishi, my collaborators with whom we are doing this work together, and the TraceS team, the team that I worked with when I was in South Africa, and my funder in Nigeria, Tech Fund Nigeria. Thank you very much for listening.
Thank you so much, Margaret, for a wonderful presentation. We have a couple questions in the chat for you, which we'll get to at the end with Mohammed at the same time. I encourage anybody else who has a question for Margaret to include those in the Q&A at this time so that, well, it's fresh on your mind. Otherwise, you can add in any other questions that you have for her at any time in the next webinar talk. So I think, Margaret, if you want to stop sharing your screen at this point, you can have Mohammed's slides up on.
Okay, great. Hey, you guys can see my screen now?
Yes, perfect.
Great. Okay. Thanks again, Gabby, and thanks, Margaret. Thanks, Gabby, for the invitation and the introduction, and thanks, Margaret, for your nice presentation. So I'm just gonna move this Zoom a little bit here. So hi, everyone. My name is Mohammed Ahmad. I'm working in the Educational Research Group at Esri Canada. I know we have many experts on this call, but just given that we might have a broad audience and different people with different backgrounds, I will start my presentation with a little bit high-level introduction about the carbon cycle in the Arctic, and before getting into details about my PhD and postdoc work. So first, I want to set up the stage here by talking about the ocean carbon sink. We know that the ocean carbon sink absorbs about a quarter of our annual fossil carbon emissions. So to really understand the ocean carbon sink, we need to think about what's actually driving both its spatial and temporal variability. So you can see the spatial variability is depicted here in this slide. You can see a region on the map with like in blue and purple color. This is a strong sink. This means taking CO2 from the atmosphere. And regions colored in red and yellow, this is kind of like acting as a source or outgassing CO2 to the atmosphere. So in the broad kind of science, I am really trying to understand this is spatial and temporal variability at regional scale, especially in the Canadian Arctic water. So to get this to this flux map that I show in the previous slide, we actually rely on field observations, especially the BC2 observations that's collected from various platforms as research ships and ships of opportunity, moorings, using CTD or Z as Margaret was showing discrete samples. Also using autonomous vehicles, sail drones, gliders, and Argo data we are actually equipped with sensors that can measure and monitor the carbon cycle of the ocean. So the observations that collected from these platforms usually are submitted to databases as Sucat. So Sucat is hosting around 34 million BC2 observations with an accuracy better than 5 microatmosphere. This is the last version of 2021. And actually the data go back from 1957 to 2021. So it's really a rich database. And here I'm showing you the graded data for the BCU2, the mean BCU2. So the regions that actually you can see was like kind of like showing you is kind of like yellow color, this means high BCU2, and things like Berber or blue color here is a little bit like low BCU2. So we know the CO2 in the atmosphere now is around 415 ppm. So you can get a sense that if the things that's above this values mean is the ocean is undersaturated compared to the atmosphere, and things below this values meaning the ocean is kind of like above this values mean oversaturated, and below this values meaning is undersaturated compared to the atmosphere. So in general, you can see the tropics regions have high BCU2, and higher latitude have like lower BCU2, or we would say undersaturated compared to the atmosphere. So it's more likely it will act as a sink, I would say. And if you focus in the Arctic here, you can see it's actually have like low BCU2 values. Of course, there is a few regions that actually you can see there is BCU2 that have like high, kind of like a high values. So this kind of like act as oversaturated or maybe outgassing to the atmosphere. To get sense of the observations, here I'm showing you the total number of observations for Sucat, for the last version of Sucat. And you can get idea, we have a good coverage in few parts of the ocean, but there is many other parts of the ocean that we don't have that many observations. And again, you can see this big, this good coverage here. This is the ships of opportunities. This we're actually equipped with underway systems that actually can collect data as it's going, traveling between continents. So, which is really great. But if you again look at the Arctic, and again, this is logarithmic scale. Just like keep this in mind. So you can see we don't have that many observations in many places, but we start getting better. Like there is start more observation coming. So more people going to the Arctic each year and collecting data, especially in the Alaskan side and the European side. You can see we don't have that much observation in the Arctic basin. In the Russian side, there is actually observations collected, but it's not submitted to Sucat. This is based on the literature. So again, keep in mind, this is just, I'm just showing how the Sucat database. So it's not like really capturing all data that is collected in the Arctic, but you can just get the sense that we don't have that much observations in the Arctic in general. Especially if you want to start looking at the unique data, that is data collected in different times of the year. So again, you can see we are mostly visiting the ocean, collecting observations in the ocean like once or twice a year, with the exception of these areas, again, that we actually, these ships of opportunities that have a good temporal coverage. And if you look at the Arctic, we can see we don't have that much observations in different times of the year. And this is for obvious reasons, logistical reasons, that we cannot go to the Arctic at any time of the year. So we have a short window during the summer that we can go and visit the Arctic and collect data. But it's started getting a little bit better here in this side. So we start getting a little bit more temporal coverage, but still we're far away from this getting this baseline and seasonal coverage in the Arctic. So the Arctic in general act as a sink. So this is based, if you look at all the papers or that actually try to budget the Arctic marine carbon sink. So you can get things varying from negative 58 to negative 180 teragram carbon per year. But if you want to actually make a good bet, I would say the average will be for the Arctic oceans negative 115 to negative 150. Like if you try to get an average, looking at all the studies as try to budget the Arctic carbon sink. The challenging here is that we don't know actually how this is changing because we don't have actually a good baseline to understand if it's actually the sink is increasing or decreasing. And this is because we have two competing narratives, I would say. The first one that the sea ice is melting, so this will increase the gas exchange and the light availability will be higher, so boosting the biological productivity, and this will increase the carbon sink. But there is also the other narrative that is competing with that, there will be increase in stratification, the temperature will be increased, and the wind and upwelling will be higher, and this will lead to high BCU2. This will lead to decrease in the carbon sink overall. So I'm looking here to giving you a sense of the Arctic shelf. So if you look at this map here, you can get sense actually that the Arctic shelves, they are really connected. So they are kind of like should be similar, but this is not the case. If you start looking at the marine carbon sink in this Arctic shelves, you can see they are really varying significantly from one to another. And this is suggesting that we need to study each one separately because the biogeochemical processes that actually driving this marine carbon sink are really different. And I didn't have numbers here for the Canadian Arctic archipelago and Hudson Bay because this was actually the focus of my PhD and will be the focus for the remainder of this presentation. So this both regions covering about a third of the Arctic shelves, and we actually have limited field observation. So we don't have that much observation, and you're really not included or well constrained when we try to budget the Arctic marine carbon sink. These two regions are really connected oceanography through the Ferry and Helka Strait. So you can just, there's a connection between them here. And they act as a kind of like a gate to transiting the Pacific Arctic Ocean to the Atlantic Ocean water. So if you look at the circulation, the water goes through the Canadian Arctic archipelago, and some of it go through the Baffin Bay, some of it going to Ferry Helka Strait and go to Hudson Bay and exchanges the Labrador Sea. And so there is kind of like linkage between these two areas. However, these two areas are really different. So especially if you start looking at the freshwater input, so the Hudson Bay, for example, have like a river input coming from all over around, and actually it's received nearly one third of Canada River discharge from around 42 rivers. And this is equivalent for, I would say, 12% of the total Pan-Arctic river input. So as a majority of river input coming to Hudson Bay is actually coming from this area here in the southern part of the Hudson Bay. And if you look at the Canadian Arctic archipelago, you can see the major river discharge coming from the southern part to the southern channels. If you start thinking about the sea ice coverage, the Hudson Bay is transition from complete sea ice cover in the winter to complete ice-free in the summer. In the Canadian Arctic archipelago, you have multi-year sea ice, especially at the northern channels, but the southern channels here actually can transition. You have like open water during the summer season. So you actually can go through the ship and go collecting your data during the summer in these areas. So how we do that? So we have access through the Canadian Coast Guard. I was fortunate, Canadian Coast Guard Amundsen ship. We have different instruments installed in the ship. We have underway systems that do continuous measurement for the BCU2 and other oceanographic variables. We also do collect discrete samples, similar to what Margaret mentioned in her presentation. Sometimes we go even off the ship and collecting data. We also have a meteorological tower to do continuous measurement for the atmosphere. So we're collecting wind speed, air temperature, the concentration of CO2 in the atmosphere, etc. So I'm going to focus here on the Canadian Arctic archipelago first. I'm showing you here the data that we fortunate to have from 2010 to 2016 in the Canadian Arctic archipelago. And I'm not going to go through details of this. I just want to show there is a special variability in this data. And I'm going to focus on 1 year in 2011. So you can see the data is actually varying from the west to the east. So you can see, if you are familiar with this area, so you can see there's higher BCU2 here in the west of the archipelago compared to the east. And if you are familiar with this area, this is because the sea ice actually is breaking up earlier in the west side compared to the east side. So there is more time for gas exchange and more time for the temperature to be increased. So this is causing this higher BCU2 here. And this special variability actually give us kind of like indications that we can use the timing of ice breakup or the timing or the period of open water period as an indication or indicator for the BCU2 variability in this area. So this was actually basically what we did. So we start looking at all the data we collect. This is thousands of measurements through all these years. And start looking at each measurement and calculating for how long each measurement actually was open water, like this, the time since the ice breakup, and what's actually the BCU2 value look like. And we start pinning this data into BCU2 and the weeks of open water, as you see in this figure. And we found this interesting relationship here, which is actually mimicking the temporal transition of the temperature in this region. So we use this relationship to start predicting the BCU2 in this area. If you actually want to learn more about how we drive this relationship and how we came up with that, I recommend it to you to go to the GOAON. We describe this in details in this paper there. So we can use this relationship to actually the timing of sea ice breakup or the period of open water period to predicting the BCU2 variability in the Canadian Arctic archipelago. And this is what we did here in this slide. So we start using this relationship to come up with a regional estimate for the BCU2 variability in the Canadian Arctic archipelago. So we can see, again, I'm showing here from 2010 to 2016. But I'm gonna pick 1 year as an example. So you can see there is here in the Amundsen Gulf, for example, we have sequence higher sink. And again, because this area usually is break up is earlier, this area, so there's more time for gas exchange. But the most of the archipelago, you can see there is not so much exchange because this area is mostly covered with sea ice and the sea ice act as a barrier for gas exchange. So there is no much exchange happening or not so much flux is happening in this area. We quantify the average CO2 flux will be around -3 millimole CO2 per square meter per day. And this will equivalent to -7.7 teragram carbon per year for the entire Arctic archipelago during the open water period. And again, if you want to learn more about this variability and how we actually come up with this regional estimates, we have this paper in GRL. You can go and have a look if you're interested to know more details. So this, for the summary of the CA, the Canadian Arctic archipelago is acting as a carbon sink and with average uptake equal to -7.7 teragram carbon per year. The interesting thing actually is that we found that the sink is actually increased in the last 40 years by 150% due to the sea ice loss and higher wind speed. So the sink was actually increasing over time in the Canadian Arctic archipelago, which was a really interesting finding to find. So here I'm transitioning to Hudson Bay, and I'm sorry I'm a little bit fast paced here, but I want to just give you a flavor of the two study areas here. So this is how the study area looked like in Hudson Bay in 2018. So actually we visited this area during the spring, early summer season. And this was a part of a comprehensive project called BASIS to try to examine the influence of the sea ice melt and river discharge on the bay physical, chemical, and biological system. So you can see here from the picture that the bay was actually, the sea ice was actively melting, but it was still intact. So it was a really interesting time. And I would say this was the first cruise actually go to the bay to collect data. So it was really interesting, especially during this time of the year. So here I'm showing you this is the BCU2, and you can get sense of the ship tracks, and this data is filtered for sure due to kind of like if the issue with the data or there is sea ice coverage. Overall, you can the BCU2's atmosphere was around 408 microatmosphere when we actually visited the bay. So anything's actually below in this color bar, that means it's undersaturated, and above its mirroring is oversaturated. So you can get sense overall that the bay was kind of like undersaturated, and the average BCU2 was around 320 microatmosphere. But we found this special variability in the bay in different regions, especially if I'm a focus here in this area close to the Nelson River, as this is estuary there. You can see there is a transition from high BCU2 to low BCU2. So close to the river, there was supersaturated BCU2, and when you go away from the estuary, there was undersaturated, and this is where the area also where the sea ice was actively melting. Looking at all observations, and this is I'm showing here the temperature salinity diagram, we can actually chemical processes are driving this is variability in the data. So this data actually is, for example, connected to the Nelson River. This is Churchill River. You can here see the sea ice melt. Usually when you close to the river, you have high temperature, high BCU2 values, and low salinity, and things close to the sea ice melt have like low temperature, low salinity, and low BCU2. And here we found upwelling and under ice observations that is characterized by high salinity, low temperature, and high BCU2 values. And looking at the fluxes, you can say overall the bay was actually acted as a low sink for the BCU2, with exception for a few areas. For example, as you can see, this is acted as a strong sink. And this because this time there was a high wind speed event that caused this high sink in this area, for example. And the average flux was around -5 millimole CO2 per square meter per day. And again, if you look at the Nelson estuary, you can see there is a transition from CO2 outgassing to CO2 uptake when you go offshore away from the river. If you want to learn more about that, I recommend you to visit this paper in Elementa. We're describing all this data and how we actually described all these biogeochemical processes that influence this spatial and temporal variability of BCU2 in the bay. So the summary of the Hudson Bay, it's acted as a, I would say, low sink is estimated by -5 millimole per square meter per day, was estimated by -3.3 teragram carbon per year during the time we visited the bay. And the bay overall acted as a weaker sink due to the influence of river water that causes kind of outgassing close to shore areas. Briefly here, I'm working now in actually turning this data into a regional estimate using machine learning techniques. So I'm using machine learning combining with remote sensing, and I'm using temperature, salinity, chlorophyll, sea ice, and mixed layer depths as a predictors to actually estimating the fluxes. So you can see along here, the shore, you can see the CO2 is actually outgassing to the atmosphere, but in general, overall, the bay acts as a sink, low sink. And again, if you go back, we can both these two numbers actually for these two study areas. So -7.7 in the Canadian Arctic archipelago and -2.3 for Hudson Bay. Based on the machine learning estimates that I did, and hopefully we're going to publish this paper soon. But this contribution from these two actually is around 7.7 to 8% compared to the Arctic Ocean. So I would say it's a significant contribution coming from these two study areas. Finally, if you are really interested in GIS and using GIS and research related to marine science, I recommended you to submit an abstract to this conference in Toronto in March. And with that, I would like to acknowledge all these people here in the list and many other people that helped me during the field work and during the lab work, and all these agencies that supported and funding my work and my projects. And with that, thank you. And I turn the mic back to Gabby if you have any questions.
Thank you so much, Mohammed. I was trying to keep up with all of your paper links, and I'm considering just dropping your Google Scholar profile and keep up with all of them. So I might do that. I might place it in the chat for people to refer to your papers. We do have a few questions coming in, so I might jump back to Margaret for the first round of questions to allow people to type up your questions for Mohammed. Margaret, if you're still on the line, we have a number of different questions. So the first one is, did you measure nutrients and oxygen? And if so, have you noticed any change in the distribution of nutrients and dissolved oxygen on your transect? That would imply some kind of change in the CO2 system.
Yeah, so I think I mentioned it during the presentation on the first both the north and the south band transit. Yes, there were measurements of nutrients and oxygen. And so I actually did not like align them to find out the change, the impact of the change on the distribution of the FCO2. But like I said, checking it just for the subtropic region where we have, where we observe the much more ocean carbon dioxide sink during the northbound transit, I do not actually see any significant difference between the two legs. So we wouldn't be able to confidently say that it is actually the Moody's aqua chlorophyll concentration data I showed for the months. It seems there's more intense chlorophyll concentration during the month of August, where we observed the change in the ocean carbon sink. So that is all the data could show. But as I said, I didn't actually check for the change as you go along the transit. Thank you. I answered your question.
Great. Yeah, and we actually had a second part to that question, which was, do you think that increasing meltwater runoff from Antarctica due to warming can directly impact the CO2 system around the latitudes that you study?
Yes, definitely. When you have melting of the sea ice, you have more of a nutrient being released, nutrients that were entrapped in the sea ice. You have more of them being released, and which will definitely enhance their productivity. And that is why we have much of productivity, biological productivity, impacting on the ocean sink during the summer. So definitely when there is runoff of sea ice melt from the Antarctic towards my region, it will definitely affect the distribution of carbon dioxide in the region. Hope I've answered the question.
Great. Thank you so much for answering both those questions live. We'll jump to one question for Mohammed and then come back to Margaret if we have a few extra minutes. So Mohammed, what is your comment on CO2 sink processes under ocean acidification, as ocean acidification may enhance atmospheric or PCO2 due to carbonate dissolution? Does ocean acidification decrease the CO2 sink, presumably in the Arctic?
Yeah, that's a really interesting question. So I think it's, I just want to say first, my work was focusing on budgeting the air-sea carbon fluxes, and I didn't do so much work related to ocean acidification. But I think was a question about related to carbon dissolution. This is something, yeah. So if dissolutions causing this kind of like increase in the enhance the carbon sink in a way. So this is something. It's a little bit. You think about it in different ways because you have more absorption of PCO2. This will increase the acidity, and this will causing a lower pH, which is causing this carbon dissolution. And so it's a little bit process that I would think it will vary from one region to another. So you can say it's sometimes in one region will be enhancing the sink, but in other regions might be really, might not be really, because it's associated with other, you need to look at it as a complete system, how the system is behaving. So it's not just one factor is causing the system to change. So you need to look how actually the temperature is changing, how the biological productivity, how everything's around this kind of a change will cause this shift, if it's going to be increase the sink or decreasing it. So yeah, so it's when you try to answer this question, you should be including all the other factors that might be causing this shift in the system. But yeah, so I think that's my answer. I'm not sure if this answers the question really, but yeah, so you need to consider all the factors, I would say.
Absolutely. Nature is very complex. I think you did a great job answering that question. And if the question asker has any clarifying follow-up questions, feel free to type them in the chat. We do have one additional question for Margaret about quality control. So did you perform any quality control measurements on for the total alkalinity and pH samples? If so, will you please elaborate on the procedures used for those two variables?
Okay, so yeah, thank you for the question. Yes, definitely. I performed the quality control on the TA and the pH. Yes, for using by using a CRM, that is a certifying reference material, which we measure first before we take the measurement of the total alkalinity. Like for each for every like 20 samples and 20 measurements, we measure a CRM to control or to check on the values of the total alkalinity we are getting from our samples. And after that, what's for the total alkalinity especially, what we did was after the measurement, we did correction on the acid correction, and using Python, the acid correction on the CRM material to value on the bottle. We use that correction for our samples. So that is how we're able to correct for total alkalinity. And for the pH, it is the reference material. After taking that of the reference material, we measure that of the pH and replicate measurement of the pH we're taking. And we have, I think the precision we have was it's a very, very encouraging value, very low value. So that is how we did the quality control on the total alkalinity and the pH. Thank you.
Thank you so much. And you broke up just a little bit in there, but I think Zoom captured all of your words at one speed or another. I have one last question for Mohammed, a question of my own. So you talked a little bit about kind of capturing the lack of baselines with machine learning today, and that's what you are focused on. I'm curious what you think about kind of the promise of machine learning versus potential promise of, innovation in autonomous sensing, and if you feel like really we need to pair the two together, or if you feel like one method would have an advantage over the other at kind of the state of knowledge that we're at right now.
Yeah, that's really good question, Gabby. I guess both of them are really needed, because if you want to use machine learning in a good way, you need to have a lot of observations. So I guess having the capacity to get access to these autonomous vehicles that actually can collect data, a lot of data in different time of the year, and going to areas that you might not have access to. So all of this will actually feed to building a good algorithm, making the predictability of the machine learning much better. So you can actually use this with kind of like with higher confidence. So for example, in Hudson Bay, in the case study, I actually rely on data that collected in a very narrow window during like the spring and the summer, and discrete samples coming from different years. So I don't have tons of observations that make it a little bit challenging to train your algorithm using machine learning and try to make it making high predictability in different areas. So, and when you try to make an algorithm, you try to make it kind of like a generalized model that could be applicable in different areas, right? So I can build a model that is fit to Hudson Bay, but I could be using it in a different area that's coastal sea, similar to Hudson Bay, and I can use the same algorithm. But with the lack of data, this make it a little bit, make you a little bit less confident to apply such algorithm in different areas. But if you have access to this data, innovative data coming from using this kind of platforms, you'll be able to do that. And I think we are going in this direction. I think we still need a little bit of few years more of this data logging in, and we can have access to this data. And I think the future is really promising in terms of using machine learning and combining with this rich data that's coming from these sensors and platforms.
Thank you so much for that answer. Well, we are at the top of the hour now, so thank you again to our wonderful presenters, and thank you to all the audience members who showed up to listen. As mentioned in the chat, this recording will be available on the GOA-ON YouTube page and just momentarily after this presentation. So we invite you to share this presentation with any of your colleagues that might be interested in learning more about the extreme latitudes and carbon in the extreme latitudes. So thank you again, and have a great rest of your day, everybody.
Thank you. Take care.
Thank you.
Bye.
Thank you.